All right, good morning. It's 8 o'clock. I know this isn't the best time for people to be um going to tutorial session for their chemistry class, since it's 8 o'clock on a Saturday morning. But circumstances have brought us here. I'm hoping I can give you a little bit more clarity as to the things that are expected of you with this unit. I think the main issue is that a lot of people are kind of overthinking things. There are a few physical fundamental principles that are kind of guiding all of this, and once you understand those principles, I think you will understand what's happening and how to answer any questions that come up with it. So I'm gonna start by going over the study guide, and then if people aren't able to make it to this afterwards, I can crop this live stream into a video that'll just be up at the same link, and I'm sure people will be able to find it. And of course, I'll be back on Monday to answer any questions. All right, so let's go through the study guide really quick. I've got the first thing you need to know is the development of the periodic table. There's not a bunch of questions on this on the test that's coming up, but it is, the idea of the periodic table being sorted or structured by periods and arranged by atomic number is very important. Um, because this can be tied in with all the other principles that we're dealing with. So the next thing you're going to need to know is chemical groups and chemical families. Make sure you go back through the notes. I'm not going to be going through this today unless somebody explicitly asks, hey, can you go over, the differences between alkali metals and everything else. But make sure you know these chemical groups, chemical families. You know where to find the alkali metals. You know where to find the halogens. You know where to find the noble gases and whatnot, because it's very important. And then be able to compare some things, like what kind of ion would chlorine be able to form versus an ion that oxygen would be able to form, um, based off of the periodic trends. So now we're getting into the periodic trends, and I think this is what's confusing people the most, is the questions concerning the trends, because it kind of involves an analysis of both of these and as well as other physical principles. So let's get into the physical principles that I'm talking about. All right. So let's see. Let's actually go here. So I've made these rules briefer for you. Um, and I think if you understand all these things, and then you understand the definitions of the terms for the different trends, you'll be able to start to piece things together. So I actually moved octet rule to the top because octet rule I feel is kind of the driving force for all these trends. Atoms want to have a full outer S and P subshell. So we should remember that what the S subshell is, what the P subshell is. Let me go all the way over to a periodic table. Actually, you know what? This is colored in S, P, D, and F subshells. So let's leave it that way. So like the blue is my S subshell, and this gold is my P subshell. So atoms want to have a full blue and gold subshell in their period. So like argon would have a full, because it contains all those electrons, S and P subshell in its highest shell. So that's the octet rule. So just to kind of give you a visual of that, let me go here. So this is one way they're going to try to do that. So neon is a noble gas and won't form an ion. Not all elements always form ions. All many elements can and do form ions, but this is just one way they try to satisfy the octet rule. So let's see. We got a noble gas, and it satisfies the octet rule. It's got 8 electrons, so 2 in the S subshell and 6 in the P subshell. let's look at fluorine. Fluorine has 7 valence electrons, so 7 electrons in that outer shell. It needs one more to kind of look like neon. So what it's going to do is it's going to try to gain an electron. So let me draw the outer shell. This is kind of like a bad Bohr model without, any regard to the nucleus right now, but that's not what we're talking about anyway. Okay, and it gained an electron, and now it looks like neon. So because it gained an electron, it now has a negative charge, but it's happy. So it looks like a noble gas. It's following the octet rule. It has a full S&P subshell. And that's what atoms are generally trying to do, is they're trying to satisfy this octet rule, which is what's driving all these trends. Now, there is an exception to the octet rule because it's not an octet. If you look at the periodic table, the very top noble gas is helium, which has 2 valence electrons. It looks like this. So the lightest elements on the periodic table, like lithium, which is a cation, which means it loses electrons and gets a positive charge. So when lithium becomes an ion, it ends up looking like helium, which I know is not, oops, that's not helium. I'm doing lithium. Lithium, which I know is not an octet. But if you look at the first row on the periodic table, it just contains hydrogen and helium. It only contains an S subshell, so lithium ions in this case, and helium as the noble gas are happy with that being their full valence shell. All right, let's go back to my definitions here. So Coulombic attraction. Okay, so Coulombic attraction, and I've shortened this to just apply to, because it's a physical principle that you're going to definitely play a lot more with when you take physics, but as it applies to chemistry. So the force between oppositely charged particles, such as electrons and protons in an atom. So, actually, let me go back to my drawing. Coulombic attraction. Or I can go here. Let's go here. Let's look at the atomic radius, actually. So, with the atomic radius, I'm sorry, I still got the hover cam on. Hold on. There we go. With the atomic radius, you can see that I didn't really draw, when I drew those elements and ions, I didn't really draw lithium and fluorine to scale. So this is like a scaled version of atomic radius, so like how big an atom is, a neutral atom is. And what you can see is that as I move across a period, so as I put more electrons in that valence shell and I put more protons in the nucleus, my element actually gets smaller. So as I put more things in, the element gets smaller, which sounds a little counterintuitive until you realize that Coulombic attraction is the force of attraction between oppositely charged particles. So electrons and protons are oppositely charged. As I add more of them to that outer shell pulls into the nucleus more, which causes, as you move down the periodic table, for the atom to like kind of crunch in on itself. So that kind of brings me into the next point, and that's nuclear charge. So nuclear charge is driving what this atomic radius trend that you're seeing. As the nuclear charge increases, I've got 3 protons in lithium, 4 protons in beryllium, 5 protons in boron, 6 protons in carbon, and so on. That nuclear charge, that total positive charge inside builds up, and it's pulling those electrons that are on the outside that have a negative charge inward, which is why you see it getting smaller across the periodic table. And of course, you see the elements get bigger as they go down, and that's simply just because they have more shells. So the second period has 2 electron shells, the third period has 3 electron shells, the fourth period has 4 electron shells. So because there's just more shells, I've got more circles around my Bohr model. The atoms are going to be bigger. But the force with which the last shell, that last circle, gets pulled in has to do with how many protons are in the nucleus. So across a period, I can be adding, over a dozen protons, which can cause the atom radius to shrink quite a bit. All right, let's go to the next idea. So that's nuclear charge and Coulombic attraction. Electron repulsion kind of is the opposite of Coulombic attraction, if you want to think about it that way. I mean, it still has to do with Coulomb's law. It still has to do with, charged particles, but it's the fact that all electrons have a negative charge. So if you put a negatively charged thing next to another negatively charged thing, so if I put an electron next to an electron, they're going to want to push apart. They don't want to stick together. It's going to be like trying to put, 2 north ends or 2 red ends of a magnet next to each other. They're going to try to spin around or push away from each other. So that is also a little bit of a factor in why we have electron shells to begin with. So we're gonna start to have more shells just to fit more electrons, because you can only fit so many next to each other before they start repulsing each other too much. Which is why the first shell can only hold 2, the second shell can hold 8, the third shell can hold 18, because remember the D block actually, these electrons start loading within the third shell. So that's electron repulsion. Electrons like to push apart. And we're going to look a little bit more at electron repulsion when we look at ionic radius a little bit. And then electron shielding. So electron shielding, let me go back to my periodic table one more time. Well, let me read the definition. So it's the reduction of effective nuclear charge. So effective nuclear charge, so the nuclear charge that outer shell is feeling. So the more protons I have, the bigger nuclear charge, and I'm reducing the feeling of that nuclear charge on the valence shell, so the outer shell, because I'm having more inner shells of electrons. So I think I should draw this. All right, let me go ahead and draw a big atom. Not really sure which one to draw. Let's go ahead and draw like krypton or something. Or well, actually, let me pick something a little bit further up. Let's draw like potassium or calcium. Okay, so calcium actually has a plus 20 charge in the middle because it's got 20 protons, right? I'm not looking at a periodic table. I hope I said that right. Pretty sure I did. Okay, so it's got like a plus 20 charge in the center. So its first shell of electrons is full in the ground state, so it has 2 electrons, and those 2 electrons feel that full force of that plus 20 trying to pull them in. But these electrons are negative. So their charges start to counteract, and they start to eat up part of that positive charge. So now, when I have my second ring of electrons, my second period on the periodic table, second shell, these guys don't feel a plus 20 charge. They feel, because of these guys effectively having a negative 2 charge, these guys effectively feel a plus 18 charge. And this is 8 electrons, which means they exhibit a -8 charge. They're all little negative particles. So the third ring is going to effectively feel only a +10 charge. And if I was drawing this better, I would actually start to have the rings kind of spread out a little bit more. Like the first ring would be closest, the second ring would spread out, and the third ring would spread out even more than the second ring. But that third ring is kind of now just feeling a +10 charge because of the first ring absorbing 2 of that +20, the second ring absorbing 8 of that +20, and this guy's absorbing 8 of that. The +10 that's left, which means my last ring, and let me kind of scale this a little bit, is going to be kind of hanging off the end. It's going to be really big. And if I go back to that atomic radius, you're going to see how big it is. I'm going to have 1 electrons, 2 electrons, and that's a -2 charge, which cancels out my +20 and makes a neutral atom. But they're not really feeling a full +20 charge. They're feeling more of a +2 charge, which doesn't pull in these electrons quite as hard as a a +3 or a +4 or a +5 charge, effective charge would. Now, as I move down the periodic table, I'm right here at calcium, I start adding protons. And watch as I add protons, gradually my nuclei, or not my nuclei, but my whole atom start to get smaller all the way to krypton, which has a lot of electrons in it. 36 and 36 protons, which is 16 more than calcium. So there's a effective charge of, well, not 16, more 7, because remember, these guys are occupying the third shell. They're not occupying the outer shell. Maybe a better example would be, sodium to argon, because I don't have to deal with the messiness of the D block here. I can kind of just skip it. So if I look at sodium, sodium's got 11 protons. So it's got a +11 charge in the middle, but that outer electron is really only feeling an effective charge of +1. So it's only being held on with a +1 charge. Whereas all the way over here, that outer shell of electrons is being held on with a +8 effective charge, because argon has 18 protons, 10 of which are the charge is being absorbed by the 2 inner rings. So that's what electron shielding is, and that's how we apply the definition. So let me go through the practice test. Since nobody's really asking any questions, I'm just kind of, going through what I think might be helpful. Let's see. Let's go through the practice test. Hover game. Which y'all should have gotten on Friday. I really hope this handed these out on Friday. If they didn't, we'll deal with that when we can. And this should kind of give you an idea of the questions you might have to be worrying about on the test. So, how is the modern periodic table arranged? How is it ordered? So we already kind of addressed this. It's arranged in periods and ordered by atomic number. And we should know that atomic number is equal to the number of protons. And then the rows or the periods are organized by when we start loading the next electron shell. So since lithium and fluorine both have 2 shells, they'd be on the same row. Whereas, what did I draw later? Calcium has 4 shells. It should be on the 4th row. Okay. keep going. All right, list all the periodic groups of families from left to right on the periodic table, associating each family with its column numbers. Okay, let's just go straight to a periodic table. This is the one that you're going to be able to use on your test as a reference. So let's use this one. So right here, everything under hydrogen are my alkali metals. So you can find this on Schoology. You can find a colored version of this periodic table with highlights and facts about all these different families. But I've got my alkali metals in group 1A. Since they're metals, they tend to form a +1 ion. And this is the most reactive group on the periodic table. These guys are very reactive, and we'll talk about that when we kind of get into ionization energy. Okay, group 2 is the alkaline earth metals. These guys are in group 2A. Because they have 2 valence electrons, they like to shed those valence electrons the same way we saw lithium got rid of one and went down a shell to look like helium. Beryllium is going to get rid of 2, go down a shell to look like helium, and have a +2 charge. Magnesium is going to get rid of its 2 valence electrons, go down to its second shell, and look like neon, and so on. These guys are going to have a +2 charge when they form an ion. And they're pretty reactive, but they're not nearly as reactive as the alkali metals. Then I have the transition metals. The transition metals are everything in the D block. You should know what the D block is, as well as the metals in the F block, which is the lowered section over here. These guys are going to have a wide range of reactivity. They're going to have a really wide range of sizes, and you're going to see like bumps in the trends when you look at graphs and stuff like that. And that's because the D shell is populating underneath the S and P shell from the row that these elements are located on. And some of the elements even have electrons in the F shell. So there's differences going on there. I want you to mostly focus on the elements within the S and P, because those are going to show us the fundamentals of what we're actually going to be dealing with. Okay, so we've got the third row, fourth row, fifth row are going to contain some post-transition metals. So this would be things like aluminum, gallium, tin, bismuth, to an extent polonium, and extending over here. So indium, thallium, lead. These guys are going to have properties similar to the transition metals, varying reactivity, usually not as reactive. Because they're kind of, their valence shells are half full. They've kind of got, less pull than these guys over here, less energy required for these guys to react and look like a noble gas than these guys. These guys have a lot farther to go. And then I've got my metalloids, like silicon and boron, arsenic, which we're not going to ask you too much about, to be frank. And then we have our nonmetals. So that consists of the nitrogen family, which is just nitrogen and phosphorus. The oxygen family, which is just oxygen, sulfur, selenium. These guys are in group 5A. These guys are in group 6A. And then the halogens, they get a special name. It's not the fluorine family, or not what you're going to see on the test. You're going to see the halogens. And the halogens are going to be in group 7A and have 7 valence electrons. So these guys, as you saw in the Bohr model that I drew earlier, these guys are going to have 7 valence electrons and gain an electron, become a -1 ion. so that they can move over on the periodic table and look like their noble gas in their row. So these guys, since they have 6 valence electrons, they're in group 6A, they're going to have to gain 2 electrons to look like their noble gas. So oxygen, to get 10 electrons and look like neon, is going to form a -2 charge when it forms an ion. Sulfur, same thing. Nitrogen and phosphorus, guess what? They're going to have to go 3 electrons, or gain 3 electrons to look like the noble gas 3 spaces over, and they're going to form a -3 charge when they form an ion. So very, very straightforward with that. But that's each family. And then, of course, we got the noble gases over here. Neon down should have 8 valence electrons, 2 in the S subshell, 6 in the P subshell, and then helium's a little special where it only has an S shell, so then it has a full S shell, so it counts as a noble gas. Okay. All right. List the groups and question 2, in order of least reactive to most reactive. Why do the groups vary in reactivity? So that is the next question that was on your practice test. So let's talk about reactivity a little bit. This goes back to the octet rule. What do elements want to do? They want to look like a noble gas. The elements that are closest to the noble gases. So they're on the other side of the periodic table, but lithium is really close to helium because helium's number 2, lithium's number 3. Sodium's really close to neon. Neon's number 10. Sodium's number 11. These guys are the most reactive group on the periodic table. So metals, things that can form cation ions, positive ions, the further I go left on the periodic table, the more reactive they are. Also, the further I go down the periodic table, the more reactive they are. Francium is tremendously more reactive than lithium. Although lithium is tremendously more reactive than beryllium or boron. So as I go to the left and as I go down on the periodic table, for metals, for things that can form cations, they're more reactive. Because if you think about it, I just need to get rid of 1 electron to turn lithium into an ion and make it look like helium. I only need to get rid of 1 electron to make sodium, get rid of 1 electron to make sodium turn into an ion and look like neon. And as I go down the periodic table, some of these other factors come into play, like nuclear charge, but the nuclear charge being shielded by the other electrons. All these guys are feeling a effective nuclear charge on their valence shell of a +1. But look at the size of lithium versus francium. Lithium is a lot smaller than, well, we don't have francium on here, but we have cesium. But it just lithium to sodium, that +1 charge is holding onto an electron even further out, which is why you saw sodium when we did that demonstration with lithium and sodium, why you saw sodium react much more explosively, because it takes even less energy to rip that electron off. That has to do with the electron shielding. Even here. Sure. Okay, well. Okay, so let's go to the next question. Let me try to get through all of these in the hour that I have. All right. List groups 1 for 4A in order of increasing atomic radius. List periods 1 for 4 in order of increasing atomic radius. I feel like we've already answered this question by showing the atomic radius chart so much. But I mean, I can show it one more time. Groups 1 through 4, 1A through 4A. So lithium to carbon. These guys are going to increase as I go to the left because my effective nuclear charge because of electron shielding, is going to be less with lithium. I have less protons. I have less nuclear charge at all in lithium, which causes the radius to expand because it's pulling in on that shell, pulling in on that valence shell less than it would be pulling in for boron or carbon. Now, as I go down, as I said earlier, I'm simply causing the electrons to have to create more shells so that they all fit due to electron repulsion. So electrons don't like to be next to each other. They're like two red ends of a magnet. So they're going to just require more space. So as I add, more shells of electrons to stack my electrons and store my electrons, I'm just going to have to create more circles if I draw a Bohr model around my atom. Okay, I think that answers that. I defined electron repulsion. I already defined Coulombic attraction for you guys. Let's move on. If you have any questions, please let me know while I'm here, because I can stop, slow down, go back as needed. I'll pull up my email on my phone as well, just in case for some reason the chat's not working and somebody needs to email me a question. Okay, so let's look at compare the listed variables, how the listed variables affect the property. So how electron shielding affects ionic radius. Okay, this is interesting. So I can look at this two ways. I can look at kind of the chart that we had in class, where y'all made these kind of like 3D models. Like this is a computer generated one. These 3D models, and look at how atomic radius is different than ionic radius. Actually, I don't have an ionic radius chart, so never mind. We're not going to even do that. I don't have the stuff up with me right now. But I do have a graph of atomic radius and a graph of ionic radius. And I know I got some emails saying this was confusing some people. I'm going to tell you a secret in chemistry. We are not going to give you very difficult graphs. We're going to be giving you graphs usually in the first quadrant, meaning all my numbers are positive. And we're gonna be mostly giving you graphs with two axes. So I've got a independent variable and a dependent variable. So, and I could look and see how my axes are labeled and see what these numbers are representing. So these numbers along the x-axis. So as my line moves down, my atomic number gets bigger. So just kind of like a periodic table. So I got like hydrogen, helium, lithium, beryllium, boron, and so on. And then I have atomic radius along the x-axis. So as my line moves up and down, my atom gets bigger and smaller. So further up, bigger the atom, further down, smaller the atom, further right, the more protons are in the nucleus. Okay. So if I look at atomic radius, and what I want y'all to focus on right now, just for this question that you're going to answer, or we are going to answer, is I want you to focus on the second period and the third period, because I'm going to compare it in the graph that's on the second page of this packet that you should have been working on. To ionic radius. Now, notice that basically as my atomic number gets bigger, as I move further to the right, my radius gets smaller. So there's a big jump between lithium and beryllium, and then it just keeps going down you know, a little bit less each time, but it keeps going down until I get to neon. And then it jumps back up as soon as I hit sodium, because that's the next row on the periodic table. I've got another valence shell. That effective nuclear charge, due to electron shielding, is now just a +1. So that's what's going on here. That's why the charge is jumping. Or not the charge. That's why the radius is jumping back up once I add another shell. But decreasing as I continue in the same shell, because also I'm adding more protons, and that nuclear charge is increasing. So this is stuff we've already talked about. You're going to keep seeing the same ideas again and again and again. Like nuclear charge gets bigger, makes atoms smaller, pulls in electrons. You know, electron shielding allows the nuclear charge to decrease effectively on the outside, so on. You're going to see all these kinds of things. So let's look at ionic radius. Here's a chart showing the second period and the third period, the ones I outlined on the first page. The radius of the most common ions of these elements. So, in this case, carbon is forming a +4 ion, which is, carbon doesn't usually form ions. I mean, it can, but it's, you know, carbon could go either way. But notice that my positive ions, my stuff on the metal side of the periodic table, is all smaller. So, I mean, I actually have numbers here. So I have ionic radius in picometers, which are very tiny, but I've got numbers that match my numbers on my graph on my first page. So picometers. So like I'm comparing apples with apples. So lithium is above 150 picometers, and now it's at 60 picometers. So it got smaller. Now, if we look at like what I drew at the beginning of this tutorial, what did lithium do when it became an ion? It literally took an electron and threw it away. The electron in that outermost shell. So that's what the metals are doing. They're taking that shell that has more electrons than they need to look like a noble gas and getting rid of them and looking like the noble gas at on the end of the previous row. So, I mean, if you think about it as if you do an electron configuration for a metal, and then you do a noble gas configuration, you're basically kicking off everything after the noble gas. I don't know if that helped anybody. So, effectively, all my metals are getting smaller because they're shedding that shell. They're going down a shell. And the effective nuclear charge on that inner shell is going to be much greater than it would have been on the outer shell because they're feeling the full force of, or more of the nuclear charge. To answer the second half of the question. Now, what's happening when I reach my nonmetals, my anion, my negative ion forming metals? So this would be like nitrogen with a -3 charge. This would be oxygen with a, oh, it's down here, but -2 charge, and fluorine with a -1 charge. Well, we can compare this to the Bohr model I drew earlier. This is not to scale, but fluorine's going to gain an electron, look like neon, because it gained an electron. It has a negative charge now. But also, electrons, the electrons repulse. So electrons like to push away from each other. And the nuclear charge didn't change. So, because fluorine as a neutral atom and fluorine as an ion have the same number of protons, that's what makes it fluorine. So that outer shell is actually being pulled in with just as much nuclear charge, but now it has an extra electron to deal with for fluorine. It has 2 extra electrons to deal with for oxygen, 3 extra electrons to deal with for nitrogen. Notice there's like a pretty big jump here. And if you remember how we filled up the nitrogen electron configuration, if you want to get really nerdy and know exactly why the jump is bigger there. So I've got 1s, 2s, and then 2p. So this is fluorine. I'm sorry, this is nitrogen as a neutral atom. What's happening here? I've got all 3 of my p orbitals only have 1 electron in them. They don't have to push away from each other that much. But then once I add my electrons to make it nitrogen with a -3 charge, this is the electron configuration that all these guys have now, because they all have a full valence shell. They all have a full second shell. Nitrogen has to add 3 more electrons in those p orbitals, and it only has 7 neutrons. I'm sorry, 7 protons. Probably only has 7 neutrons too. Those aren't as important right now. But they only have 7. It only has 7 protons, which means with 7 protons, it's trying to keep in 8 electrons in its outer shell, which it can do, but it's struggling a lot more than oxygen fluorine, which has 1 and 2 more 1 and 2 more protons in its nucleus. Okay, let's continue. Let's keep going. All right, ionization energy. Okay, cool. I've been wanting to get into this. Ionization energy. I did not understand the back. Okay. All right. Well, the back of the test, or the practice test. I hope that's what I'm going over right now, and I hope I'm clearing it up a little bit. So, I mean, like if I wanted to write down what's going on here, we just saw the difference between the ionic radius and the atomic radius. So electron shielding, these both stay the same because I'm keeping the same atom. So these variables stay the same, except how would you find which family it's in using mole, and how do you calculate it? We're not really concentrating on that right now. We're more working on how to identify the differences between atomic and ionic radius and the interatomic forces that are dealing with that. So we've got electron shielding and nuclear charge. So electron shielding is how the inner electrons are basically stealing the full force of the nuclear charge from the outer electrons. So this is going to be the same for all those. So these actually effectively don't change. What does change is I start to have more electrons. And as I add more electrons, my nuclear charge is not as sufficient at pulling them in, which is why my anions tend to expand, and my cations, since I lose an entire shield, or I lose an entire shell, there's not as much shielding. So if you look at lithium, the shielding is only coming from these inner 2 electrons. Once I form an ion, I don't have any inner rings of electrons. I just have a ring of electrons. So let's look at ionization energy. Okay, let me hide this really quick. Go back here, and all of these charts, I've linked this website to your Schoology page. So if you want to start looking at like all the these 3D models of all these trends, that can be pretty helpful. So it's asking you about the ionization energy, how the electron configuration and the nuclear charge affects it. So let's look at the electron configuration of lithium versus the electron configuration of beryllium, since they're right next to each other here, right? So we won't do questions like the last one on the breakdown for success. Yes, we will. How do we find out what family is you? Oh, I understand your question. Yes, that's actually on the bottom of this practice test. So yeah, so the questions like the last one on the mole actually has to do with the ionization energy, and it's measured in kilojoules per mole. And I'll go over the definition of ionization energy once I'll go over it right now because we're talking about ionization energy. So ionization energy is the amount of energy required to remove an electron. So as you can see, these guys are the lowest, so they require the least amount of energy to remove electron. That is linked to reactivity. Not the only thing that's linked to reactivity, but is the most powerful thing linked to reactivity, which is why the alkali metals are the most reactive elements on the periodic table. These guys require so little energy to get an electron to jump off of them, and for things like lithium to shed that shell and look like helium. They're just so close to becoming to having electron shells that look like the noble gases and fulfilling the octet rule that they're really happy to do that. So they have very low ionization energies. Now notice that this says the first ionization energy, and then I've got, I'm getting ahead of myself. Let me just stick with that. So let's go back to the practice test. Let me get through this question so I could answer Ultimate Content Creator's question. I'm not sure who that is, but I can get there. Okay, so we've got ionization energy. How does electron configuration affect it? So that electron configuration affects it in a very direct way. If I do an electron configuration for sodium, it's going to end with S1. In this case, 3S1. For potassium, it's going to end in 4S1. For rubidium, it's going to end in 5S1. I've got one electron in that S shell. And once I get rid of that electron in the S shell, it's going to bounce back down to the previous noble gas and look like that. Whereas as I go up on the periodic table, I've got to, these guys have valence electrons in the third shell, which is why they're more or less even. But as I move up my A groups, especially, so like calcium to aluminum to silicon to phosphorus, I have to get rid of more and more electrons in total to look like a noble gas, which is why it takes a lot of energy to get fluorine to remove an electron, because it's, it doesn't want to get rid of 7 electrons and look like helium. It wants to gain 1 electron to look like helium. And then the noble gases are really high because they're already happy. They're already fulfilling the octet rule. There is absolutely zero reason for them to want to get rid of an electron. So that's how it applies to electron configuration. How it applies to the nuclear charge is pretty simple as well. As I increase on my periodic table across the period, I get more nuclear charge, right? So those protons that are added, sodium has 11 protons, magnesium has 12, aluminum has 13, and as I keep adding protons, that nuclear charge is pulling on the electrons more, which causes more energy needed to be added in order to take one out because of Coulombic attraction. All right, electron affinity, and then I will answer your question about the increasing ionization energies measured in kilojoules per mole. That you will have a question about that on the test. That's correct. So let's here. Electron affinity. You know what? Actually, let's change this because I think it's going to be more helpful to to talk about electronegativity. Electronegativity. So electronegativity, you can find in your notes, is defined as the likelihood of a atom to gain an electron, or the power an atom has to gain an electron. And if you remember, I don't have a graphic for this pulled up right now, but fluorine is the most electronegative element. And the reason for this is because fluorine is only one electron away. If you look at ionization energy, it's only one electron away from looking like neon. So it's very likely, it has a lot of power to gain an electron. So the electron configuration of all those halogens that are going to have a very high electronegativity are going to have an almost full valence shell. It's going to be, like S2. So in case of fluorine, it's going to be 2s2 and then 2p5, which is really close to what neon has, which is 2s2 and 2p6 in the valence shell. And then as I start taking electrons out of that p shell, like oxygen, my electronegativity goes down. And then nuclear charge again. Fluorine has one more proton than oxygen. It has two more protons than nitrogen. So since it has a bigger nuclear charge, it's more likely to attract, it has more power to attract that electron. I hope these questions are getting answered for you. By, talking about the definitions that that I identified at the beginning. Okay, so ionization energy. This is, I think, was your question, and this is kind of what I wanted to end on because it was a little bit more complex. But it is something we expect y'all to know. So let's go back to the presentation real quick. So notice that with this ionization energy chart, this is the first ionization energy. And this question 9 and 10 is very similar to the question on the breakdown of success. It's very similar to questions in the packet that we're asking you to analyze these things. So this is the first ionization energy, which means it's the ionization energy is the energy required to remove an electron. So this is the energy required to remove one electron. So if I look at look at the next slide, second ionization energy, this is the energy required to remove the second electron. So notice what happened. So these are my alkali metals. They're the most reactive. They really want to get rid of an electron. And then they don't. They are now the highest column on the periodic table because they've already removed an electron. They've already dropped down, dropped a shell. They've all done what lithium did here and dropped their outer shell and now look like a noble gas. So these guys are happy the way they are. So they're going to see a huge jump in ionization energy between the first and second ionization energy for alkali metals. So sodium is an alkali metal. Now look at from the packet that we were working on in class. Sodium has an ionization energy of 495. I know I didn't include units on here. I apologize. That might have been confusing some people. I'm glad I did include units on the practice test. But sodium has 495.8 kilojoules per mole for the first ionization energy. So the energy required to remove one electron. And then to remove the second electron, it requires 10 times. So 4,562 kilojoules per mole. So hopefully I'm answering your question at this point. So you can see this jump right here, the difference between these two ionization energies. And even if I cover this up, you should be able to tell this is an alkali metal. It is okay. It is not going to require too much energy to get rid of one electron, but once I remove 2 electrons, or once I try to remove the second electron, it is taxing me 10 times the amount of energy to get rid of that electron. It is really not happy to get rid of that electron. So, if this theory holds, magnesium, which is in the second group, should be relatively happy. Now, the second ionization energy does go up. The reason for that is because of nuclear charge. So magnesium has an extra proton, right? So its effective nuclear charge is actually +2 on the valence shell because of electron shielding versus the nuclear charge, which means, you know, it's going to be a little bit more hesitant to get rid of its second electron. But look at the jump. So it goes from 1400 to 7,000. So it went from 700 to 1400. So, you know, it doubled. And then it went to 7,000. That's the jump. So even if I covered this up, you should be able to say this is in the second group. This is an alkaline earth metal. I don't know what alkaline earth metal it is, just based off of these numbers, but I will be able to tell you it's an alkaline earth metal. That'll form a +2 ion and then be happy at its +2 ion because it really doesn't want to get rid of its third one. So in this case, aluminum, look here. So I've got 577.5, 1800, so a little bit more than magnesium to get its second one. So that looks like a jump, but then I look at the next one, I'm like, oh, was it a jump? It was kind of a jump, I guess. But then it should be very obvious because look at the difference between 2,700 and 11,000 kilojoules per mole of energy. So you're going to be able to look at the difference between removing 3 electrons and removing 4 electrons and say this is in group 3A. So let's go to our chart on our practice test and try to answer this. And this is directly similar to a question you will have on the test, and be able to justify. So I have first ionization energy of 419, and then a second ionization energy of 3,000. That is already a pretty big jump. And then if I look at the jump between the second and third, it's not as much, right? This is a 1,400-ish difference, and this is a 2,500 kilojoule difference. So if you're still with me, hopefully you're guessing that this is where my jump is. This is an alkali metal. It is not super fussed about giving up that first electron, but it really doesn't want to give up the second. Not saying justify your answer. I kind of just did that by talking about how the biggest jump in energy is actually between the first and second ionization energy, between getting rid of one electron and getting rid of the second electron. That's the biggest jump in energy. These jumps are not as big because I'm starting to remove energy from the next shell down at that point. Okay. I'm hoping this gave you a lot more information, a little bit more guidance to help you finish your packet. I hope you have a good rest of your weekend, and I'm going to go ahead and trim the front of this video and leave it up for people to kind of follow along with for the rest of the weekend, and then we can talk about it as I get back to class and you get back to class on Monday. Again, these 5 things really explain how all the periodic trends drive, and these 5 things drive the periodic trends. So make sure you know these things, and then make sure you do also know the definite definitions of the trends, specifically atomic radius, ionization energy, and electronegativity, because those will be the most common things that pop up. And be able to look at a blank periodic table and start to like visualize these trends. I hope you have a good rest of your weekend. Thank you, those of you who engaged and helped drive some questions that I hopefully answered. And have a good